Racing cars are flying around a circuit. Hang on a minute. Something's not right. Look closely and you'll see one of the cars doesn't have a driver.
When they're out there now, the autonomous car knows exactly where it is and it can stay on the line. And that is your first part. The second part is your LIDAR and your radar, which is sending out radio waves and light beams to detect where the barriers are, but also where your other drivers are, where your car is, I should say, not your other drivers, one driver at the moment. And that is what the autonomous car on the last lap could obviously detect that, slows up, saw a space and went through.
These specially modified racing cars are participating in the Abu Dhabi Autonomous Racing League. Although the racing doesn't yet have the excitement of Formula One, it's a leap forward, pushing the boundaries of autonomous vehicles.
The stuff that we're doing may enable luxury manufacturers to be able to put in components that could allow a wider audience to get more out of those cars than they currently can. I mean, your average driver may be very restricted in their capabilities of using that car safely, and the technology we're developing could actually, because of its ability to prevent accidents occurring, could be very useful.
Luxury cars driving themselves are a long way since Leonardo da Vinci first mooted the idea of self-driving vehicles in the 16th century. That's right, Leonardo was into self-driving carts and came up with a clockwork-powered three-wheeler with a pre-programmed steering system. It took 5 centuries before historians in Florence, Italy, built a machine using Leonardo's blueprints. Not unexpectedly for a Da Vinci design, it worked. However, it wasn't until a century ago, in the 1920s, that any serious effort was made to make a driverless vehicle. Electrical engineer Francis Houdina's trials in 1926 were groundbreaking for the time. Using radio to steer and power a car as it traveled through New York. More remote control than autonomous, the experiment ended in disaster when the vehicle crashed into another car carrying photographers capturing the event. Move on another 70 years and the Europeans got into the autonomous vehicle game with Eureka's Prometheus project. Government funding to the tune of €750 million saw a consortium of universities, automakers and tech companies create self-driving vehicles. In what was, in essence, a feasibility study, the team managed a 1,000-kilometer journey on crowded Parisian highways, altering speed and changing lanes successfully. Moving on to the turn of the century, technology was catching up to the dream. And that's when the US Department of Defense got serious. The DARPA research arm had previously funded projects involving semi-autonomous vehicles. It backed Carnegie Mellon University's NavLab 5, which successfully piloted its way from Pittsburgh to San Diego. A driver handled the throttle, the brake, and the computer brain the steering for almost all the 2,850-mile journey. But things took off when DARPA created the Grand Challenge in 2004. The aim was to spur innovation by offering a $1 million prize to a team that completed a desert course with an autonomous vehicle. In that year, none of the 15 teams competing was successful. The following year, the team from Stanford University in California drove away with the upped prize money of $2 million. The success and innovation encouraged hundreds of startups to enter the sector and bring self-driving vehicles to the streets. So, what is an autonomous vehicle?
We like to think about it in sort of a binary fashion. So, for folks who are very familiar with it, they'll know that there are kind of 6 levels of autonomy from, level 0, which is, no level of autonomy, all the way up to level 5. But going through each one would take some time. Let me kind of break it down in maybe more of a binary way. Which is that you either require a sober, licensed driver who's awake and ready to take over or do the driving task at any given moment, or you don't. And so the first one would be sort of levels of autonomy up to level 3. In levels 4 and 5, you require sort of none of those things. You don't need a licensed driver. You don't need a sober or an awake driver. The vehicle basically performs the entire driving task.
According to autonomous vehicle guru David Silver, getting that level of autonomy has 3 distinct components.
Sense, plan, act. Kind of it's a three node cycle. You sense, you plan, and you act. And that's really how autonomous vehicles work as well. Autonomous vehicles are basically a big robot. And the system starts by sensing. You have lots of different sensors: camera, radar, LIDAR, the typical sensors on an autonomous vehicle, though you may also have other sensors. And from those sensors, you try and build an understanding of what the world around the vehicle looks like. So that's kind of the sense part of the sense, plan, act cycle. And then we move to the planning part. Now that we know what the world around us looks like, what's the plan that we want to make to navigate through that world? Do we want to turn left? Do we want to go straight? Do we want to speed up? Do we want to slow down? And that's the planning part of the sense, plan, act cycle. We build that plan in accordance with what we sense the world around us to be like and what our goals are for moving through that world. And then once we have that plan, we have to actuate that plan. We have to bring that plan to fruition by, in the case of an autonomous vehicle, turning the steering wheel, pressing the accelerator pedal, pressing the brake pedal, and that's the act part. And then once we've actuated that plan, we start the cycle all over and we go try and sense, what does the world look like now that we've moved a little bit and time has progressed forward? What do we sense the world looks like now? What should our new plan be based on our new sense of the world? And then how do we act based on that new plan?
Many companies, including Waymo and Cruise, have already been offering autonomous rides. All used adapted models of vehicles we see on the road daily.
It is a suite of sensors that are on the outside of the vehicle. So cameras, LIDAR, radar, and microphones that are outside and can kind of sense all of the things that are important for the driving task. And then on the inside of the vehicle, we have a very powerful computer that can take in all of those inputs, kind of synthesize it for the machine to understand what's going on in the world around it, and to safely plan a path through that so that it can, as I mentioned before, get our riders from one side of the city to the other.
But getting from A to B isn't as easy as you would think. All the autonomous vehicle pioneers have the same challenges.
On the hardware side, right, so just building out the sensors, there are a lot of challenges in being able to create sensors that can kind of perceive the entire world and be able to give that kind of information back to the machine. We're extremely proud of the hardware that we've built and packaged together to equip these vehicles with the ability to see. Perception, so being able to see and hear all of the things in the world around it, is also a big challenge once you get those inputs from the sensors. The world is a confusing place, and so that's why we utilize the 3 different types of visual sensors that I mentioned before: LIDAR, camera, and radar, so that they can all sort of aid each other and kind of build off of the things that they're really good at and give our machines an understanding of what it needs. And then on the audio side, right, being able to hear sirens and things like that are really, really important for navigating in urban environments. Being able to hear kind of around the corner, et cetera. Behavior prediction is another big one, right? So, if a car is, traveling in a certain way and it's predicted to, come across our path, one thing that you could do is just say, well, always hit the brakes, right? But, that might not work well, right? Especially if you need to know that that vehicle isn't going to interact with us or is going to stop before it crosses our path, or vice versa, right? Knowing that a vehicle might interact with us, and so being able to take any kind of evasive action or just hitting the brakes there. And then finally, path planning, right? So being able to figure out, based on what we see in the world around us, the behavior of all of the other vehicles or vulnerable road users, pedestrians, cyclists, et cetera, how to safely plan the path through that so that you can make progress and so that you can get from point A to point B safely. And everything that I've mentioned there is in optimal conditions, right? But then you've got rain and fog and sandstorms, even in one of our environments in Phoenix. And so being able to handle all of those conditions and be able to continue to operate a service throughout all of those is yet another challenge.
And it is AI that's helping the driverless car become more efficient.
Maybe 10 years ago, people might have said that the hardest part was perception, was seeing, sensing. And that some people might say that's still the hardest part. All of the parts are hard. I hate to say any of them are easy, but we have made great strides in perception. In particular, perception has proven to be to dovetail very nicely with advances in machine learning. So a lot of the things you read about in the newspaper, in the news about machine learning, about things like ChatGPT, a lot of those approaches work very nicely with things like camera data and laser data to figure out what does the world look like. A lot of the same techniques actually map between chatbots and working with computer vision and other sensors. And that has helped us progress really far along in terms of sensing. The planning part, which is where I work, I think is a big challenge because there are lots of different layers of planning and there are lots of different approaches you can use. And I would say, unlike perception, where machine learning has really become the consensus approach to figuring out how to sense the world, there isn't yet really a consensus approach to how to plan through the world. In some parts of the planning problem, like say the mapping problem, like what does the turn-by-turn navigation look like? There is some consensus around using things like graph theory, kind of the same techniques that you might use in the mapping app on your phone. But then there are other parts of the problem, like should I speed up or slow down right now? Do I think this vehicle next to me is going to cut me off? Where figuring out how to approach that problem and make sense of the world and make a plan for how to move through the world is still really an open question. And that makes planning a really fun part of the sense, plan, act cycle. And then the act part is really mathematically oriented, figuring out exactly how much to turn the steering wheel, how much to press the different pedals. That's a part of the problem that engineers, particularly mechanical engineers, have been working on at automotive companies for a long time, and we're able to apply a lot of the work they've done for things like cruise control, which you might have in your own car, to autonomous vehicles.
And that mechanical learning is finding its way into aiding passengers too.
I think it's most helpful to talk about kind of the Waymo driver as opposed to a particular vehicle, right? Because one of the huge advantages of the Waymo driver is the fact that it learns from the experience that it gets from all of the vehicles that are driving. So, we were one of the first applications, certainly the first widespread application of AI. And our training data set is primarily composed of our autonomous vehicle, our autonomous miles, our human-driven miles, and things like that. And so we are learning from every single one of the miles that we're driving. On top of that, our vehicles can share interesting information that they see in particular locations that happen in the moment to other drivers in the fleet. So for instance, if we drive by a road and there's a big road closed sign and cones all over the place, we can tell other vehicles that are in the city at that time, hey, this road is closed. If passengers want to get picked up or dropped off near there, they're going to need to pick a different spot like that. So yeah, so very much like the Waymo driver, think about it as kind of an entity that's learning and growing, as opposed to something that's happening on a per vehicle basis.
The teething problems of autonomous vehicles roaming the streets have been obvious. Any accident has grabbed headlines. There have been plenty of bumps and scrapes, and the only death directly attributed to a driverless vehicle was 6 years ago. GM's backed Cruise halted self-driving operations after regulators pulled the plug following a serious accident with a pedestrian in 2023. But that hasn't dampened industry enthusiasm or the overall safety record.
Over the more than 10 million miles, many human lifetimes of autonomous driving that we have done, we have had the opportunity to benchmark our performance against what a representative human driver would have done over those same miles. Right, we partnered with a third party, Swiss Re, which is a big reinsurance provider, and what we found was that for each mile that we're driving, we are several times safer than a human. And so when you add all of that up, to date, we believe statistically that we have prevented 28 injury-causing collisions. And so, on the one hand, you might say, wait a minute, 10 million miles, only 28, that seems like a pretty small number. But I would say that if you're one of those 28 people and you don't have a broken leg, you don't have a concussion, you're not in the hospital, you can still play with your kids and do all the things you want to do, that is life-changing.
As self-driving vehicles learn from each other, could they all become perfect drivers and take the fun out of driving? It's something the autonomous racers have been toying with.
Somebody came to me and said, gosh, you're going to make it boring. Every race is going to be the perfect race and all the cars are going to do the same thing. And I thought, gosh, that's an interesting one. There are a number of modules in the programming. There's the localization module and so forth, where you learn the track, and then there's the various control modules for actually operating the actuation and so forth. But then the critical one is the planning or strategy module. Like anything, that is essentially, how do you drive this car? What approach do you take to going into that corner, exiting from that corner? What preference do you have for risk? And that's going to be built into the programming. The team that are programming the car are going to build that into the car. So there's going to be a bit of human DNA in there. Now, over time, of course, the car learns and it perfects, but it will always have that bit of human DNA into it.
So what does the future hold?
In the short term, we kind of see a bunch of different trends. So one thing is that autonomous vehicles are on the road right now in a few American cities, offering driverless rides. And I've taken driverless rides in San Francisco, and they're phenomenal. You get in the vehicle, and there's nobody else there, and you tell the vehicle where to go, and it just drives you wherever you need to be. And Waymo is expanding nationwide, as are other companies like Zoox, Amazon's autonomous vehicle company, and Cruise, my former employer. A bunch of these companies are starting to offer robo-taxis in a bunch of different cities nationwide. So that's one thing that I think we'll see over the next few years, is the number of cities that have autonomous vehicles where regular people, not just employees or beta testers, but you or me or anybody can download an app and call an autonomous vehicle. The number of cities where you can do that will expand in the US, and I think in the next probably 2-3 years, international. So that's super exciting on one front. I think another front is autonomous trucking. That's the industry that I work in right now. I think we'll start to see autonomous trucks hauling freight probably on specific routes initially. In the Southwest, between specific cities where companies feel really confident hauling freight on the highway. And then we'll see those routes start to expand as well over the next few years. And then the third area where I imagine we'll see progress, and in fact I'm sure we'll see progress over the next few years, is in driver assistance. And these are not fully autonomous vehicles, but these are vehicles that have what's called adaptive cruise control. If you've ever driven in a car where you can set the cruise control to say 100 kilometers an hour, but it will slow down if there's traffic ahead, and it will speed up when the traffic eases. That's what in the industry we call adaptive cruise control. And lane keeping and lane assistance. And those features will become more and more advanced to the point that vehicles will be able to change lanes for you, and they'll be able to do more off-highway driving. Right now, a lot of driver assistance happens primarily on the highway. We'll start to see that expand more into surface street driving. And so you'll see advances kind of on all three of those fronts, I think.
In the meantime, it's full throttle ahead for those developing autonomous vehicles. However, a stricter stance by regulators may stamp on the brakes.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.